ILOG Discovery is an application and a software component that lets you analyze and manipulate large datasets in a visual and intuitive way. It features a full set of tools to import data from various sources, create rich and expressive views, filter and manipulate the data, annotate it, edit it, and create live or static reports. This video introduces the visualization engine used in ILOG Discovery, its power of expression and ease of manipulation. We will show how views are created using a simple, unified visualization model called linear state data flows. This simple model allows creating a full range of visualizations using a simple point-and-click user interface. In ILOG Discovery, you visualize a data table. The rows of these tables are the objects to be visualized, here a collection of US cities. The columns, shows on the top row of the screen, define some data variables. Here, these are the city's name, its state, its population, as well as a number of statistics for each city, such as crime rate, education index, average housing cost, climate index, and so forth. On the right-hand side of the screen, you see a number of parameters, such as X, Y position, color, width, and height. These are the image variables. In the center area, you see a view that is the result of matches made between the data variables and the image variables. Right now, this view is not very interesting as we have not made any such match. The cities are laid out on a grid, and it is still possible to see individual values by moving the cursor over each square in the view. Working in Discovery involves assigning image variables to data variables, or vice versa. To start with, we assign a decoration value image variable to the population data variable. We obtain a visualization often called the heat map. Next, we assign a sort image variable to the population data variable to sort cities by increasing population. This produces a rainbow-like display that indicates a normal distribution. A few orange values indicating small population, a mass of light blue and green indicating the average city sizes, and a few more purple and red rectangles for the big metropoles, New York, LA, Chicago. All the interaction needed to build sophisticated views happens in pretty much the same way. Choose a visual attribute and map it to a data column or to an expression, or choose a data column and assigning it to one or more visual attributes. Besides coloring and sorting, the most useful attributes are the coordinates of the graphic objects. To obtain a regular 2D graph, we can choose to assign two columns, for instance, latitude and longitude, to, respectively, the x and y coordinates of these rectangles. We can make the size of each city proportional to its population using the width and height image attributes assigned to population. Of course, we can refine the view to show scales, add some margins, add transparency, and change the shapes to ellipses. Once we have obtained our 2D graph, we can save it for later reuse and come back to a previous view. The default visualization assigns a single shape to each data object. It is, however, possible to assign several shapes to a data object and to control their individual attributes with data variables. Here, we create some rectangular shapes inside each city's rectangle and make their height to be proportional to some data attributes of interest. For instance, we choose the economy, arts, education, and transportation attributes. We obtain a small bar chart for each city in the 2D graph. This view can help assessing how some criteria are correlated with one another and distributed geographically. Now, instead of placing the bars side to side in a bar chart fashion, we can make each inner rectangle height constant and its width variable. For example, the first histogram would become the second barcode-like figure. Rotated counterclockwise, we obtain a vertical barcode for each data object. Next, we can set the height of each data rectangle to a full constant height and its Y origin to be the bottom of the view. We add a legend to display the column names in front of each bar line in the barcodes to obtain a distributed histograms visualization. This view displays the distribution of 4 criteria along longitude. Notice the less densely populated areas of the Middle West and how eastern cities tend to have a higher education index. The view starts to look like a parallel histograms, also called matrix file, a view made classical by Jacques Bertin to help analyze datasets. Yet, we need some more features to transform this view into irregular parallel histograms. To obtain parallel histograms, we use the pack horizontally macro. Macros perform in one operation several settings that can be done individually. This macro makes the view change from distributing values according to longitude to placing all the objects next to each other in the order defined before. This macro assigns what we call local variables to the x and width image variables. A variable has a name, an initial value expression, and an iterate expression. To create a parallel histograms view in an imperative programming language, we would write something like this. To achieve the same effect in Discovery, we do pretty much the same thing interactively, knowing that the loop is handled implicitly. We create a variable named total and a variable named cur. The x and width of the image variables are assigned to those local variables instead of being assigned to data variables. ILOG Discovery, as it goes through the records, will evaluate the iteration values for each variable after drawing each record. Thus, the loop over each record is implicit, like in a data flow architecture, but a side effect is introduced when each record is drawn. Now, let's start again from a copy of the initial view. Suppose we are not interested in seeing statistics for each city, but instead want to study the states each city belongs to. To this effect, we can use the group operator to create a grid of US states. The view parameters are the same, except that all root objects are now the US states. It is possible to obtain the same graphs and histograms we have obtained for the cities, but view only graphs of states. Note that the view settings are applied recursively, so that within each state one can still view the cities arranged in a grid. Using variables and iterators, also defined with macros, it is possible to transform this grid into various kinds of tree maps. Regular slice and dice tree maps, laid out according to the number of cities in each state, or according to the sum of the populations, or various kinds of scorified tree maps. All those views are obtained using a combination of three local variables that control the display parameters. We keep a copy of the current tree map view and finally revert this image to a grid. We have mentioned before that the same layout parameters have been applied to each state recursively to lay out the cities within each state as a smaller size grids. It is possible to choose different representations for the inner portions of the grid. We create a sub-projection, either for all states or for selected subsets, that will display the cities according to a different choice of viewing parameters. For instance, we choose to define a 2D graph of housing cost versus climate for each state in a dataset. This sort of view is useful to help compare some trends in between states. For instance, note that in some states like California or Washington, there is a correlation between both variables, whereas in other states like Colorado or Alabama, there is no such correlation. By using other shapes than rectangle and ellipses, it is possible to create other types of graphs using the same base principles. Here, a parallel coordinates visualization is displayed. It uses a polyline shape, whose image variables include a sequence of x and y coordinates. The x coordinates are assigned a fixed sequence of constants, 0, 1/10, 2/10, and so forth, while the y coordinates are assigned to some chosen data variables, population, education, crime rate. Furthermore, ILOG Discovery lets you interactively build fully custom visualizations and create combinations, such as this tree map embedding a sequence of bar charts. With some practice at viewing tree maps and charts, it becomes possible to use the sophisticated views that show both detail and structure information. This helps users construct the representations that best suit and highlight the important aspects of their data. Of course, ILOG Discovery does not require a regular user to recreate the most popular views from scratch each time. Rather, a view creation dialog presents a set of predefined views, provides some hints about the possible uses for each view, as well as the most useful parameters to set for each view. Multiple views of the same datasets can be viewed simultaneously. Because all views are built using the same visualization model, all interactions and visual feedback are performed using the same generic and multifunctional interactors and methods. This provides a full set of functionalities to visually analyze datasets. The user is given access to a wide range of visualizations, but has only a minimal number of concepts to learn. This presentation has introduced the linear states data flow model and shown how it can be put to use to create numerous sorts of views in a seamless and intuitive manner, using only a few base principles. These data flows define four operators: partition, sort, assign graphic primitives and decorate those primitives. Those operators are applied to the input datasets either selectively or recursively. Iterators and local variables augment the data flow with state handling capabilities. You can obtain more information on ILOG Discovery at www.ilog.com/preview/discovery and download the free preview version there. Other videos in this collection covers various aspects of ILOG Discovery. What is visual data analysis, how to edit large datasets using Discovery, and various business applications of ILOG Discovery. Thank you for your attention.